Hello, this is Mr. Wyrick. I'm here to talk to you today about lesson 10.5 over tangents. Tangents are a specific line that will go out near a circle and touch at one point. Okay, so make sure you get tangent. It touches at one point, and that's called the point of tangency. If you have a common tangent, that's the first concept that they bring up in this. A common tangent is tangent to more than one circle. They could be directly next to each other and the circles be tangent themselves and the line goes through there, or it could be there's a circle over here, there's a circle over here, and we are tangent running along, or it could be, they're on the same side, it's a line that goes like this. Any which way, as long as that line is tangent to more than one circle, it is a common tangent. As we move forward, we have Theorem 10.10. A line is tangent if and only if it forms a right angle with a radius drawn out from the center. We know a radius is drawn from the center out to the side. So if our point of tangency here, we draw a radius out to it and we can measure, and that makes a 90-degree angle, then we know it's tangent. If we can look at a triangle that's on there, count up the other two angles and say, okay, well, this radius comes out to this line, but it's at 85 or it's at 107, then it's not actually tangent. It can't be a tangent line. It may be drawn to look like it's tangent, but it will not be tangent. A lot of them would intersect in more than one place, so you have to be careful on that. On 10.11, Theorem 10.11, two segments from the same exterior point, if they are both tangent, then they are congruent. So I've got my point here, point B. It could be very close, it could be a very extreme angle, or it could be very far out. It could be a very small angle here. But as long as both of these segments coming from B to where they would touch, we could call this one CB and call this one DB. So if BC and BD are both tangent, then they are also both congruent up to that point. They're coming from the same place. They intersect that circle at a 90-degree angle. You can tell if you have to do a proof on this one, you could draw a line down through the center here from the center of the circle to point B and find out that, okay, let's say these are 90-degree angles here. We have this angle bisected and that angle bisected, and this side would be equal to itself. These would be the same. So we could have hypotenuse leg, or we could have side angle side there very easily to prove those triangles congruent. And if they're congruent, then BC and BD would be congruent by CP, CTC. So it's not a huge leap of logic to come to this one. Don't forget, we did talk about earlier circumscribed polygons. If it's inscribed polygon, that means we have a circle and we have like a square inside of that circle. That one would be inscribed. But circumscribed is the opposite. We have this circle and then we have a square that goes around that circle. If you have a circumscribed polygon, no matter how many sides it has, it is tangent on each side. If you remember back, Harry Potter, that nice Deathly Hallows symbol, each one of these on the outside of that circle, showing off my nerd here a little bit, it would be tangent at each one of these points. It only intersects once, and we'd have a nice 90-degree angle to look at there. Okay. If there are any other questions about this, most of your questions on this one are going to be, they're equal, you found out they're tangent, check the angles, that kind of stuff, same kind of thing that we've been working on as far as properties of circles. If you have questions on these, make sure you come in and ask about it. The problems that we will do is numbers 9 through 34, and then number 36. If you have questions over them, you don't understand what's going on, you've reviewed this, whatever. If you don't get it, make sure to come into tutorials or ask me during class. We'll see you then.